I'm officially starting the recording now, so we're going to keep it clean from here on out. So Zoomers, you can see me, hear me, see my screen. We're all good to go on that score? Excellent. We can't see your screen. Why not? Is it the smart board that's not smart? Okay, it should be. There we go. Easy fix. Yeah, it's on here, which is why I didn't even look behind me. All right, technical difficulties been resolved. So yes, look at all that's left here. Yes, two weeks of lectures and then finals week. So for those of you who, anyone do track and cross country like in high school, college?
Track.
Yeah, I did long distance running, and in track, the last lap of the race, they always ring a bell to let you know it's the last lap. And so that's what I feel like. I can hear the bell ringing, like we're not done running yet, but we know it's going to happen soon. And I feel like I just passed the end because we just had this nice few days off, and I could feel myself like unclenching, right? And now we're like back in it again, but it's the last lap. We got the bell, we're going to make it. So this is a good time for me to remind you of what is still out there to be completed this semester. Nothing due right now, but do you want the good news or the bad news? The bell is anxiety provoking. Oh, I don't know. I enjoyed the bell.
Yeah,
Bad news? Okay, your homeworks for homework 4 are not graded yet.
That's okay.
That's okay.
I'm not sure if that's bad news or good news. It's bad news for me. Maybe my perception of good and bad is questionable in this example, but no. I'm about 2/3 through. I'm spending time on them because each person's data analysis, I have to get my head into what you're doing, what your variables are, like what it means, and that takes cognitive effort. So I'm trying not to rush through them so that I can provide decent feedback. The same will be true for the ChatGPT assignments, although there's a lot fewer of those. So those are not yet done. I anticipate finishing them tomorrow or Thursday by the latest. Revisions, if you feel like doing them, will be due at the end of finals week. So you'll have at least 2 weeks to work on those if you choose. The good news then, you do have stuff to do now anyway. Yay!
Yeah, you got it mixed up.
I got it backwards. Maybe it's from my perspective, because that means that my work in getting them ready for you is done, and now it's on you. So what I do have for you is your very last formative assessment is launched this morning. You should be able to answer the first 2 questions now and the 3rd question by the end of the week. And also your very last homework is ready for you to attempt. Now this takes a minute to explain. As noted on here, homework 5/6/7. These models, as you may have anticipated, do not converge onto correct answers that match 2 decimal places across packages. So you will do either 5, 6, or 7 because it is the same assignment with the answer key from different programs. Okay? So only one of these 3. If you want to use SAS, that's homework 5. If you want to use Stata, that's 6. And if you want to use R, that's 7. And the instructions at the top only have the starter syntax in that form of the software, and they have a reminder. So I will aggregate all the scores across the 3 and count it as 1 homework. You only have to do 1. Okay? Fair. And that is due at the end of finals week as well. So good news, bad news. Office hours. So finals week we are not meeting as a class. However, I am having office hours on Monday and Wednesday afternoons when I normally would have. I am also having office hours during the time I would be teaching. So 12:30 to 2 on Tuesday and Thursday. Cass is not having office hours but offered to answer questions over email or have individual meetings. Nikki is having office hours on Tuesday only because she is leaving the country, I believe, on Wednesday. Both of you are. So long journey after that. So that way, if you have things that are outstanding, you want to get caught up, lots of contact hours to be able to do that. Hard deadline, 5 o'clock on Friday. If it's not in by then, it doesn't count. Yes.
What material is homework 6 over?
Homework 6 is based on example 6A. It is, yep.
As it says right there.
As it says right there, yes. It is a binary problem, binary outcome multi-level model. It is actually based, it's an extension of a homework that you may have done in a previous class as a single level model, actually. So, it's not the golfing one. It is predicting the logit of getting a job based on your level of quantitative training and number of publications.
Oh, wow.
So this is a not a preschool example this time. This is a current events kind of example. Spoiler alert, quantitative training is good for you. Yes, because when you simulate the data, you control the world. So. All right, any questions about outstanding stuff? Or what's left? We're good to go? All right.
In the past, when students get their homework back, right? I mean, it's probably fairly comprehensive, the feedback, so they're like able to do it in good time, you know?
Yes, so I will let you know via email when the homeworks are available. You will download them from the homework portal. That's why I had you name the files in a certain way, because I create a dynamic link that goes to each of your homeworks. You will get a score, and you will have a whole bunch of comments and probably some edits too, asking questions or clarifications, reporting what's missing. Of the ones that I've graded so far, people lost points for not doing stuff. Like for instance, I asked for intra-class correlations for every level 1 variable. Several folks did it for only the outcome. So my note would say, you're missing some, do those. Several people, I would say most people, did not give me a figure. And you're like, yeah, I know, I didn't want to do it yet. Okay, so you want your extra point, do your figure. If you get your score back and you're like, yeah, you can keep your 1/4 of a point, I'm not doing this, fine, I can live with that. So yes, if you will get feedback as to what you need to fix. If any of that is unclear though, please ask me, because I'm happy to clarify as needed, or I may have just missed something that was there, and if it was there, then I'll fix it. When you do your revisions though, please make sure that you leave in my comments. You can mark them as resolved, but leave them in, because I want to see what I asked you to fix. Because if there's something that you missed and I didn't catch it, I don't want to penalize you the second time because I did miss it. So think of this as like, only change what I'm asking you to change, and if you use track changes, then that makes my life a lot easier, because then I can easily see what you did. If you need to fix a table though, and it's going to have like 8,000 track changes, just don't do that. Just put in a new one. So, a question from the Zoomers: why do the results not match in different programs, and how to decide which result is better while analyzing data? So results don't match across programs because of differences in how the likelihood function is optimized. It depends on who coded it and how they did it. And the other thing that can differ is integration points. So for instance, in Stata, I tried to do the homework using 1 point of integration like in the other packages, and it threw up. It wanted more. It just wouldn't converge. It's like, okay, you can have more then, whatever. In practice, I would, if you're ever in doubt, you might try the same model in different packages to get converging evidence. But if you see very, very large values for either the estimates or the standard errors in generalized models, that's usually a sign that it has no idea what that parameter should be, and you probably don't have enough information to estimate it well. You might want to take that out. One thing that I like in using SAS Glimix that I have not found in other packages is an option to show the gradient for all the parameters, which is the first derivative for that parameter in the likelihood function. If it's truly at the top of the function, the maximum, then the derivative should be 0. And so looking at those numbers can give you an indication as to which parameters are causing the problem. But that's not, as I said, that readily available. Okay, other questions? So yes, to answer your question, if you don't know what to do, please ask. Does that seem fair?
Yeah.
I'm not trying to make it like more difficult than it needs to be or mysterious. I'm trying to be transparent. But in all honesty, learning how to take feedback and respond to it is a really important skill. So I want to give you practice with that too.
And it sounds like, based on the current sample size, there hasn't been a lot of OMG, what were you thinking? Or just like, you forgot this, please.
Yeah,
Please
a
resolve.
whole lot of this is missing for losing points.
That's encouraging.
Yeah. Yeah, I think so far I don't really have, other than that, like I said, that's the big one. But I'm not done with grading yet. So that's based on my even more limited sample out of the 23 of you. Anything else while we're on the topic? Other questions? Okay, then are we ready for lecture 7? Yay! This is the mic drop lecture. That's what I'm going to call this. Because you've heard me say before, if you have a hammer, then everything's a nail. Everything is a multi-level model, including measurement models. So this lecture is interesting to me because I have struggled to find a home for it across the different classes that I teach. The last time that I did this, it was in the factor analysis class. I think that was way back in Nebraska, though, was the last time I had time for it, because I had more classroom hours back then. And now I've stuck it in this class because I know there's at least a few people in this class who are analyzing experimental data in which this is the approach that they would use. So it's a different kind of clustering. It's the idea of subjects and items as the units of clustering rather than groups, but it readily translates into everything else that we've talked about, so I thought I would throw this in here. The other reason that I'm presenting it is because next semester, there are a large number of you who are taking either the item response theory class or the factor analysis and structural equation modeling class, or both. And so this is somewhat of a precursor, a foreshadowing of what you will see in that class and how it really does relate to what you're learning this semester as well. So away we go then. So this is the premise here. These are Legos. We all know what Legos are. You probably stepped on them if you haven't played with them, or done both. But the way that I think about quantitative methods is as a series of building blocks. And which blocks you need for a particular problem depends on the problem. But if you understand the building blocks, then you can put them together in whatever way is going to be most optimal, such as this pile of Legos turning into this lovely creation shown in, I believe this is from the Mall of America. So the 4 blocks, as I see them: linear models, estimation methods, link functions, which we just finished talking about, and then number 4 here is the one that I'm focusing on, random effects, which are the same thing as latent variables, otherwise known as latent traits, latent factors, latent constructs. They get different names as a function of how they are used and for what purpose. If, in this class, we are using random effects to build in expected correlation among the outcomes from the same cluster, or we're modeling dependency doing that. B, if you're talking about latent variables, you would use those to model unobserved constructs that are thought to cause a series of item responses instead. It's the same machinery, just different words, different notation for different purposes and different contexts. So linear models is number 1. It's the most basic building block of any analysis. It answers research questions. Is there an effect of a predictor on an outcome? Is it the same for everybody? Or does it depend on other predictors? Does it vary across clusters? Is that effect still there after controlling for X, Y, and Z other things? No matter what kind of outcome you're predicting and no matter what kind of sampling design, linear models work the same way. And that's why, as I note, I have drilled them in every class. No matter what class it is, you're going to get practice doing this because it's really, really important to be able to answer your questions. To be able to add more blocks, though, we need to switch into different methods of estimation. So least squares type stuff is just fine if you have a single level model where the outcome is supposed to have normal residuals. That's the only situation in which you could use least squares estimation. Technically speaking, you can consider random intercept models a part of that too, but that starts to fall apart when you have unbalanced data. So we switch to maximum likelihood, or Bayesian estimation, which is maximum likelihood with the addition of priors for the parameters. What other blocks you need then are going to be determined by what kind of outcome, which gets us towards link functions, and how many dimensions of sampling, which then we build in random effects or latent variables for. So in most cases, designs that you're going to analyze are going to not just be single level. They're going to have multiple dimensions of sampling. So multiple outcomes, multiple people, multiple clusters, multiple occasions, multiple items, and so forth. And so these different kinds of sampling introduce different kinds of variability. So if I think about it in the context of repeated measures, which is really what this is about, even though we're thinking about items as what's being repeated, then I might have a model like this. let's say that repeated measures are different occasions in this context, in which I have 4 occasions observed for each person, and what I'd be trying to do is figure out how much of the variation across time is due to between-person constant differences versus how much of it is time-specific within-person deviations. So this is the context in the longitudinal class. In our current class, the way that you would think about this is that the boxes would be people, and part of the people variation is actually between clusters, and the rest of it is within clusters. Same idea, just different terminology. This is exactly what happens in measurement models as well. So if we think about our repeated measures not as occasions, but as item responses, then we're trying to figure out how much of the variability across items is due to the characteristic of the person answering the items, their latent propensity towards whatever these items measure, aggression, ability, anxiety, and so forth, whatever it is. The idea is that the way that a person is causes their response to these items. So there should be a commonality, a dependency. But yet then there's also, why did you answer this item this way after controlling for your trait? Well, I don't know. That's just item-specific error. This is the same thing. Random effects are latent variables. So if you understand that connection, then you can build in whatever system of random effects or latent variables you need to address a particular problem. So random effects is what we call this idea when we are trying to handle dependency, when we are trying to build in common sources of variance of people from the same cluster or occasions from the same person. We can have multiple sources. So we talked about cross models, for instance, where we would have maybe children nested within primary schools and within secondary schools, or we could have time-varying groups, children changing classrooms over time, that kind of thing. And if you're in this world, you would call this type of model that contains random effects a multi-level model, or a mixed effects model, or hierarchical linear model. If you're on the other side, if you're talking about predicting item responses and trying to figure out how many dimensions underlie your item responses, so how many different reasons are there that a person would respond the way that they do, how many different traits are you measuring, then we're talking about latent traits as doing the exact same thing. It's still a circle, it's still unobserved, it's still a term that is person-specific or cluster-specific whose variance we estimate, but then it's for a different reason. So the connection here is that if you have normal outcomes and you have latent variables, then that is what confirmatory factor analysis, CFA as it's abbreviated, or structural equation modeling is for. If you have categorical outcomes, ordinal, binary, nominal, and latent variables, that is what item response theory is for. They are mechanisms by which we can avoid listwise deletion of incomplete data. We can try to use all the data that we have. We don't have to aggregate if we don't want to. And we can quantify and predict all the different sources of variation across people, across clusters, across items, across whatever. Okay, how are we doing so far? This is like big picture-y stuff, so that's all. Big picture-y. There are a lot of connections across the different models and across the different classes, and I very rarely get the chance to try to make them explicit, which is what I want to try to do. So I want to tell you a story that illustrates some of this here. It's a true story. These are the characters in the story. They are. So this is Jim, this is Larry. I went to graduate school with them at KU in Lawrence, Kansas. So this is a shot of downtown Lawrence here. And one night after work, we were out playing pool and trying to console Larry because he was bummed because he had a paper rejected. So we were asking him what happened with the paper. And he said, well, my F1 and my F2 weren't significant, so they wouldn't take it. So the background to this, Larry is a psycholinguist, He studies psycholinguistics. So that is all about how different properties of words, Charlotte's like, woo, represent. Yeah, Charlotte's gonna like this story. Different properties of words influence people's ability to process them. So in these types of experiments, they would carefully select and or manipulate words for various quantities, like how frequent they are, how long they are, neighborhood density, how many other words are around them. This is me hand waving because I am not a psycholinguistic person. But his stimuli were all words or non-words, and usually it was how quickly they could identify whether it is a word or a non-word as a function of all these different word features. And in that point in time, which would have been 2002-ish, there was an ongoing debate in that field about how to best analyze the resulting data from these experiments. Should they use an F1 ANOVA or an F2 ANOVA or both? And I had never heard these terms before. I was like, well, I know ANOVA, but I didn't know there were F kinds. Like, what does that mean? So he explains it to me. So in this type of design, here's a simplified case where I have items that are varying in 2 dimensions. So let's say we have low and high on one dimension and low and high on another. And you would come up with a bunch of words that would fill each of these cells. So let's say there's 100 words of each kind. So there's 400 in total. An F1 ANOVA is what I would call repeated measures or within person ANOVA, where the first step is to aggregate the items that are within the same cell up to one mean, and so each person would have 4 means that would then be analyzed. So in this type of model, you would put in a main effect of dimension A and B and their interaction. You would have a random intercept for persons, because that introduces a correlation of the 4 means from the same person, which should be, and then you'd have some kind of residual. The other one, which is the one that I was not familiar with, is what's known as an F2, where the aggregation happens in the opposite dimension. So in this perspective, we aggregate over people, and you would have a mean for each item. So this is a between items ANOVA, because items are independent. And so then you would not have any random effects, because all items are treated as just a single level type of design. So Larry's paper was expected to show that the effects of A, B, and their interaction were significant both this way and that way at the same time. And in his analysis, only the F1 was significant, the F2 was not. So at the time, I had just started trying to learn multi-level models, and I was like, hey, I think I can fix this. So what if we do a multi-level model where items are nested in people, okay? So then we can have our level 1 model that has these A and B item features. Here's my random intercept. This is going to be great because you don't have to aggregate over anything. You can use all the data, which means that any missing responses are assumed missing at random rather than completely random. You don't have to have categorical predictors. You can have continuous item features. And I was all excited about this until I realized, yeah, this is still wrong. This is the whole data version of an F1 ANOVA. And I didn't initially realize this until I was sitting at a conference and someone else presented a model in which they did it the right way. And I was sitting there going, oh, that's what it needs to look like. So we fixed it, we wrote a paper, and I'm happy to say that we are one of the first papers on this topic. And from what I understand, Charlotte, you can correct me if I'm wrong, the way of analyzing these sorts of data has turned almost exclusively into mixed effects models, and this F1, F2 thing is gone. That's what it seems like amongst the people that talk to me, at least. Yep, she says. Okay. And who else is here? Is it Tolga, I believe, has these sorts of data sometimes too, but with eye tracking. So mixed effects models have become much more popular. But here's the problem. The way that I was approaching this was from a longitudinal perspective, where I was thinking about items as within persons, and then level 2 is between person. But in the same way that I knew that we had to control for person dependency because some people are just faster across the board at all of these items, some of these items are easier than others. It's the same. So what I really need to do is split out what I was thinking of as purely level 1 item variation into 2 things. Differences between items as their own random effect, and then the remaining residual, which is trial level variation. Why is it that this person responded to this item in this way, even after controlling for their general ability at this, and the item's general difficulty? That's what level 1 should actually be. So you know this as a crossed random effects model. We did this in unit 5 in this year, where we had schools crossed with neighborhoods and primary schools and secondary schools and all that stuff. Remember that? That's this. That's the exact same model for a different sampling design. So the way that I would approach this now, and the way that we approached it in a paper, is to say that response time for level 1 trials with nested within level 2 persons who are crossed with level 2 items, that's the way that I would describe this, is a function of, in this case, some general intercept for some kind of average response time. You can put in your item predictors, and so note that this is 00123 because item is the third subscript. So this is the first, second, third predictor of item variance. And then we have our variance for variances left over here. Red person ability is what I'm going to call this. Why is it that this person is faster than all the others? I don't know. We can predict that with people variables. Item differences that remain after controlling for which kind of item it was. Why is that item responded to faster on average? I don't know. Has to be something else about that item. And then E is trial variation. So why is it that this trial was faster? Maybe it was the first trial and they hadn't gotten bored yet. Or maybe it's the last trial and they're really well practiced and now they can do it well. So trial level predictors can be included to explain residual variance. People things can explain person random intercept variance, and item characteristics can explain item random intercept variance. It's the same exact premise. Okay, now how we doing? Question?
Yes.
Okay.
Well, I don't know if it's a question, but I just want to consolidate what I think you're saying.
Okay.
So on the previous slide, you essentially were treating all items as the same. Or not the previous slide, the previous model that was still wrong.
Right. Let me go back to it.
Yep, so this is essentially like all models are, or items, excuse me, are measuring a construct the same.
Items are exchangeable, and they do not vary systematically from each other. So there's no variance across items, like per se, on average, is what this model says. Does that sound right? Okay. Yes, so we're ignoring differences between items. We're pretending like they're all exactly the same, which in some experimental settings could be the case, but when you're using real-world stimuli like words, that's probably not going to be true. Okay. So we did a paper using different data than the one that was rejected because he had another data set in which they had roughly the same number of people and the same number of items. So that was advantageous. So this is a 2007 paper or so. The example that goes with it I posted in October. So I did a workshop where I used that example, and I think I've given it in class before. There's also a very similar example in chapter 12 of my textbook. So those resources are there. I've got another example for you that I built just for this. So we have response time to decide if it's a word or not, in which most of the time they get it right. So there's very little missing data due to inaccuracy. There were two predictors, low versus high phonological neighborhood frequency, which it's like how many words sound like it. Can I get the psycholinguistic people in the house to weigh in on that definition? Kind of, okay. You want to correct me? Have the same phonemes. Okay, I'll accept that. Large versus small semantic neighborhood size, like number of words that are related to it based on meaning? Yes, okay. Well, let's just call them A and B, shall we? Is that good enough? A and B are item thanks. So in his data set, first thing I did was an empty model, just like usual, except that I have two different kinds of random intercepts. So the partitioning of variance that I ended up with, 24% of it was because some people are faster than others. That's person random intercept at level 2. 11% of it was because some items are responded to faster than others. That's also at level 2 in the item random intercept. And then 65% was something else, not systematic to the person or the item, something about the trial and the unique combination. So let me ask you this. All I have in my data set from Larry are these two variables, which are item things. Best case scenario, what is my total R square in predicting response time? Let me give it a second, let y'all think about it. I have 2 item predictors. That's it. Best case scenario, how much variance in response time am I going to get?
11%.
11. That's it. So this is a situation in which total R-square is probably not a useful effect size because we're not even trying to get the other 89%. It's going to look terrible no matter what. This is a situation in which pseudo R-square of the 11%, how much of it is due to A and B is going to make a lot more sense. And it turned out that 30% of it was due to A and B, which yields a total R-square of about 3%. So if we think about that, 30% of the reasons why some items were responded to faster than others is because of these 2 known characteristics and their interaction. That leaves 70% up for grabs. And when we showed these results to Larry, we were like, I thought you said you like balanced these items. He's like, well, yeah, we controlled for this, 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 and this. Like, why aren't those variables in the model? At the time, they weren't in the model because they weren't like characteristics of the design. He didn't want to turn it into a 2 by 2 by 2 by 2 by 2 by 2 by whatever. But in this type of framework, you can throw in any item predictor so that you can soak up that extra variance and improve the power to detect the things you do care about. So it can be a continuous variable, it can be a categorical variable, it can be anything. Plus, do you think it might be interesting to see whether some people are faster than others for reasons? Like individual differences? Sure. Some other field of psychology would be like, actually, yeah, that's what I do for my research. So it's like, do you care about the red part, the blue part, or the purple part, right? These are different disciplines, but you can do all of it at once. And I have a note here that F2 ANOVA was closest to the MLM results. Do you know why?
Because items were the main part of the study?
Because items were the story. So let me back up for just a second here. Do I need to? Yeah, let me get back to the models real quick. This one. So F1 ANOVA aggregates over items and treats people as random. So by collapsing across all of the items within the same cell, we are making an untested assumption that they're all exactly the same. There's no systematic differences between them. They're all equivalent, exchangeable. But people are not exchangeable, so they get a random effect. The opposite then, the results from the multi-level model were very close to the F2 because this is an item level model, pretending that people are equivalent. We didn't have any people predictors with which to say otherwise. Question. Let's see, in-room question, then Zoom question.
I'm just curious, when you're doing this, like, using software or you going like Beautiful Mind, like on the window or...
Okay, no, I will never be writing equations or doing derivatives by hand.
Okay.
All of this is done by software.
Okay.
I don't think the F1 and F2 ANOVAs could conceivably be done by hand because those are all, after you do the aggregation, that's least square stuff.
Mm-hmm.
Like in the 1950s and 60s, you would have had to do it by hand. But all of this needs to be found iteratively. So we've lost the hand part of the story.
Right. I wasn't trying to make you seem old. I didn't
Oh, I
know
am
what
old. I am
grad
old.
school is like when you're in it, like what you used or whatever.
So the difference is that when I went to grad school, there was a computer lab that if you wanted to do any work, you had to physically go and sit in that lab. By the time I became a postdoc, we had like remote desktop as the new cool thing that I was like, oh, I don't have to go to my office? Like I can do it from home? And now you're like, I can do this on my phone. I can do this on my iPad. So yes, I am old, but not quite that old.
Lisa, I have a question about the
Yes.
item analysis.
Yeah.
So by items, do you mean like specifically different types of neighborhoods, or is it just the conditions themselves? So there are only 2 options.
Good question. By items, I mean the different stimuli that people are reacting to individually, and
Okay.
the ones that are the same kind, that are both like low frequency and small size, like that would be a cell, but there would be, 39 divided by 4 of them, roughly.
Okay.
Yeah, that's an important distinction because the ANOVA world doesn't think about individual items, it thinks about item conditions. And the single value that would go into the analysis is the mean across items of that condition, which even me and my terrible math skills know that 39 does not divide into 4 evenly. So that means that there's at least one condition that has fewer items. And in certain combinations where it's really difficult to get an item that fits that combination, there may be many fewer than in other combinations, which further exacerbates the problem because then there's differential reliability for the condition means. Comment from the Zoomers, fixation is different, other people. I do not know what that means, but I'd like to know. Did the other Zoomers have questions? No. Okay. All right. So yeah, and more generally, this is true. If you are interested in testing why people differ from each other, people need to be a random effect in your model because there has to be room for there to be people variance left over with which to evaluate the effect of your people predictors. If you're interested in testing differences between items on purpose, there has to be an item random effect in your model so that there can be item differences left over to evaluate. And I did a simulation that I reported in my book to try and make this point. And I have a couple other papers along these same lines that I can share with you if anyone's interested, but they're a little bit dated at this point. Okay, other questions or comments? So the goal of this is just to show you so far that the same skills and setup that you're familiar with can be used in other circumstances. Now, I see this as being really useful in a lot of real-world situations in which you can't make your items comparable exactly, but you want to control for them. So, for instance, if you're giving children passages to read so that you can measure their reading fluency or the number of words per minute, like I know that that's a thing that my son had to do when we got his scores in our parent-teacher conference, then you want the paragraphs to be comparable in difficulty, right? You don't want to give somebody a hard paragraph and another kid an easy one because obviously the kid who gets the easy paragraph is going to look more fluent. But how easy is it to make paragraphs that are exactly equal in difficulty? It's tricky, right? So the best you can do is maybe randomly assign or counterbalance or try to spread it out so that there's like whatever differences would wash out. But what if you could control for that difficulty? What if you could keep track of exactly what paragraph a child was given and factor that into your analysis? What if, right? This. That's this. I'm gesturing to all the screens right now. This. So if you think about reading fluency as the target outcome, that's a person characteristic, right? Right? Person skill. That is another name for random intercept of people. We call this a random intercept. Next semester, in the IRT class, you're going to call this theta. At the beginning of my factor analysis class, you're going to call this a factor. It's the same damn thing. So if you're interested in measuring differences in children's ability to read fluently, and you have to do it with passages that differ in their difficulty, you could have passages as the item, children as the people, and you could do everything at once. And if you can control for differences in passage, like maybe number of words it has, or the reading level of the passage, or other characteristics, then that can help reduce the variability due to differences in passages too. Fixation is important to reading. Yes, it is. Okay, I get your point now, I think. So when would you need to worry about this in practice? Well, not if the item variation is fully explained. So there are a couple situations in which this would happen. One would be like in Larry's design where I have 4 cells, A, B, and then low and high of each. What if I only gave them 1 word per cell? Could I do that? Give them 1 word of each kind. Would that be a good idea? Probably not. But if I did that, if I go back to the boxes here, these boxes, what if there was only 1 item in each box? I could still do A and B in their interaction, but then there'd be nothing left over. So then I don't have to worry about ignoring item variance because there isn't any. Putting in A and B and the interaction, that's 3 degrees of freedom. There's 4 items. The intercept is the 4th. It's done. It's saturated. This is the same idea as controlling for clustering via fixed effects, right? If I only have 5 different schools, put in school ID as a fixed effect and call it good. Then you've controlled for all the differences. Same idea. If you give each item its own set of fixed effects, then you also don't have to worry about this. And this is the connection to measurement models. In confirmatory factor models, which are latent variables predicting continuous responses, or item response theory models, which are latent variables predicting categorical responses, each item gets its own characteristics. In CFA, each item gets an intercept and a factor loading, which is the slope relating it to the trait. In IRT, it gets either that or discrimination, which is a slope on a different scale, and difficulty, which is a threshold or intercept rearranged a little bit, but it's the same premise. But in those cases, if you give each item its own fixed effect, that is like saturating the model. That's like controlling for clustering by putting in clustering ID. And I'll show you how to do this in multi-level modeling software. So in traditional psychometric models, where each item gets its own set of fixed effects, we don't need to worry about this. We also wouldn't need to worry about this if the items are things that are unique to a person. So if you're looking at eye movements, right? I can have eye movement 1, eye movement 2, eye movement 3. I can guarantee they're not going to be the same 1, 2, 3 as someone else's eye movements. Those aren't items. Same thing if you ask somebody to list maybe their 10 memories from their childhood. We're all going to come up with different memories. Or speech utterances. Those are all going to be unique too. So there's no real potential for item differences in this situation either. When this starts to matter is when we're concerned about exchangeability across items and/or we want to try to predict what makes some items more difficult than others. And this is relevant when taking experimental tasks and trying to turn them into psychometric instruments with which to measure differences in personability as well as differences in item difficulty. That's the connection. Okay, 118. How are we doing? Maybe? Maybe? So sideways is the goal here. Sideways is the goal. What I'm hoping for is at some point at the end of next semester, those of you who are in the psychometric classes are going to look back at this and go, oh, that's what she was yammering about. I just want you to have seen it. This is the part of the semester where I'm exposing you to things but not asking you to do a homework on. Yay for that, right? This is the, and that's not all, part of the deal. And that's not all. So let me give you a little bit of a crash course. This is my mic drop. Everything is a multi-level model. The IRT folks will tell you about this thing. It's called a 1PL. 1PL stands for one parameter logistic model. So you know the word logistic, right? It means it's using a logit link function. It's doing that because it's predicting a binary response. It has one parameter, which is item difficulty. And in this way of writing it, if I write it predicting probability, it looks a little weird. The logit version is a little cleaner. I have theta, that's this new thing here, which is a person parameter, minus b, which is an item parameter, and the minus sign means that this is scaled in difficulty, such that higher values indicate lower chances of getting it correct. This is a separate fixed effect for every single item. It's not obvious from the notation, but that's the way that it's meant to be interpreted. So in this version of talking about it, we would say that your chances of getting the item right depend on your level of ability working against the difficulty of the item. Okay, so this is a psychometric model. This is also a multi-level model. Same damn thing. If I write it this way, then I'm swapping out what the psychometric folks would call theta as my latent variable and replacing it with my random intercept for people, which is also a latent variable. It is the same. Theta is a random intercept. The idea that each item gets its own fixed effect, I have expressed using a more standard linear model notation, where I1 is a dummy code for whether it's item 1 gets a 1 if not, as 1 if it is, a 0 if not, through all the way up through however many items we have. So this is a model in which there is no general fixed intercept. I kicked it out. Instead, what I have is an item-specific intercept, where if this is item 1, then this one turns on and the rest of these turn off. If it's item 2, this one turns on and the rest of these turn off. So these are like little light switches flipping for each one. So this is the same model, just a different way of writing it, with one catch: plus signs rather than minus signs. So the difference is that these intercepts are indicators of easiness, not difficulty. Higher values mean a higher probability of getting the item right. But you know how you turn them into difficulties? Switch the sign. Yep. So this is the same connection as intercepts and thresholds. Thresholds are difficulty parameters. Intercepts are easiness parameters. In this model, each item is given its own intercept. So all the differences between items are already represented with the fixed effects. There is no item variance left over. So this is considered, do I have, yeah, okay, I have that in the next slide. Yep, say that next. So items are fixed and people are random in this model. You can estimate this using standard IRT software. I will show you how to estimate it in Glimmer. And in MELogit, I think, in Stata as well. And Sask Linux, or any multi-level modeling package that has link functions. Okay, for identification then. So this is a word you have not heard me say in this class, because we've always done it the same way. What is the scale of a random intercept? What's its mean?
0.
Always 0, because the mean is given by the corresponding fixed effect. Random effects are deviations from fixed. They always have means of 0. What's the random intercept variance?
We assume it's constant.
It's constant, but we let it figure it out, right? Like a number shows up on your output, and depending on the scale of the outcome, it could be 6, it could be 0.6, it could be whatever it needs to be. Okay. Our random effect / latent variable is identified by having a mean of 0. It's estimating a variance, which means that there is an implicit 1 in front of this theta here. In other versions of this model, identification is different. So on the psychometric side, if you fit what is known as a Roche model, that's this method of identification. Mean 0, estimated variance. If you fix the implied slope here to some number other than 1, make it the same across items, and then fix the variance of the random intercept to 1 instead, that's called a 1PL. It's the same damn thing. They are the same model on 2 different scales. The generalized version corresponds to the Roche version because we estimate the variance of theta, but we keep the mean to 0. So here's Lego number 1 then. What if I wanted to predict why some items are harder than others? Could I do that? Sure. The same way that I could predict why some of Larry's words were responded to faster than others using response time, I can do that for accuracy. So I can build in a linear model that predicts item difficulty here. This is a really old model. I'm going to try and get it right. Yeah, I wrote it down so I didn't have to try and get it right. Yay me. Future me appreciates this me. Linear Logistic Test Model, that's what this stands for. It was made in the 70s, just like me. I was made in the 70s. I was. I am that old. Thank you very much. So in this model, that's what they're trying to do, is build a regression for why it is that some items are harder than others. So this can be construed, by the way, as evidence for construct validity. Like, if you know what your construct is, then you should be able to control what makes people slower or faster or more or less accurate in responding to things. You should be able to quantify and predict differences in difficulty. So let's write this weird-looking IRT model as a multi-level model. And forgive me for the red and the blue. These are older slides where I didn't have that same thing, and I ran out of colors. So I've used all the colors that I have that would render on white background. So my linear model with my item predictors is right here. So this could be, you know, phonological whatever and neighborhood whatever, A, B, all the way up to whatever. And then here's my random effect of people, my theta, my person random intercept. But what's not here?
Residuals.
Yeah, there's no residual because we're in logits. But the other one, there should be something else here.
Item characteristics.
We have some item characteristics, but not one for each item. These are just item predictors.
A random intercept for items.
Yeah, we're missing the other U that should be here, a random intercept for items. Because otherwise what we're saying is that this line of predictors perfectly explains why some items are faster than others. Responded to faster, in this case, more accurately.
Lisa,
Yeah.
I have a quick question. Because for us, random intercepts in previous classes, we said those were like specific deviations from blah, blah, blah. However, here, well, in this case, random intercept represents the specific estimate for some person, or are we assuming that these are just numbers that can be estimated for each person?
So for people, there's nothing in the model that predicts why some people respond differently than other people. So this random intercept for people, this theta, is unconditional. So that would be just like how far off you are from the average. But in this case, because we have item predictors, an item random intercept that will be here, I think, on the next slide, very soon, if not now. This item predictor would be the U that's left over. So it's like based on the item characteristics, that would get you up to some level of difficulty, and then that would be the difference relative to where it actually should be based on an empty model with no predictors.
Okay.
So it's the same idea, but just on the item side.
Okay, so here we are not estimating those latent things. We just can use that random intercept to represent some kind of variance in those random scores. Okay.
Yes, and here is the thing that trips me up when people talk about like person parameters and item parameters. There are no person parameters. Theta is not in the likelihood. Theta variance is in the likelihood.
Yeah.
You don't need to know what theta is for each person to be able to figure out everything else. But you do have to integrate across it to figure out everything else.
Okay.
So this is the idea of solving by numeric integration, where we try and what if my theta was this? What's my probability? What if my theta was this? What's my probability? And then summing across all of those weighted combinations. That's how you would have to figure out the rest of the model. Once you have the rest of the model, you could go back and try to predict theta for each person, but it's not a parameter in the same way that item effects are parameters.
Great. So that's why at the end we have that variance tau square OPO
Yep.
in our model. Okay.
Yep. This is a person variance. This is what creates item variance, but this is a very strong assumption. So let me show you an example from not Larry, but the same time period. This is my dissertation. It was about old people and driving. I know, you're like, what? Yeah, I used to be a cognitive psychologist. Don't tell anyone. I'm not actually a statistician. I'm a psychologist. Sort of. I can't help people unless it's with their data. But that's what I started, going into undergrad. I'm going to help people. And then I, took some clinical stuff and I did like some volunteer work trying to help counsel people. And I was like, no, I'm not. Okay. What's next? So now I do counseling about statistics.
It also helps people
Yeah, I'm helping people still. It's just, like I still have I had a couch in my office, my old office, and I had Kleenexes. Like I was still sort of doing therapy. It was just with data, about data. My model won't converge. That's a problem to be solved. Anywho, back in the day, I did cognition and attention stuff, and my dissertation was trying to create a measure of visual search ability for use with older adults in the context of driving. And to do that, I hijacked a task that our lab had used, which is known as a flicker paradigm change detection task. Have you seen this before? So the way that it works is I drove around, or excuse, I didn't do the driving. I was in the passenger seat where my then boyfriend and family drove all around the Kansas City metro area and the Omaha metro area, and I think Topeka. We went to a bunch of different places, and I took pictures from the passenger seat of road pictures just like this. So you can see this is right outside Kansas City. And then I took Photoshop and I changed something in the picture. So when they're right next to each other, it's fairly obvious what changed. Do you see what's different?
Took me a long time.
Took you a long time. Well, to be fair, you're in the back of the room and you're not driving and it's a small picture, but you're in the exit lane. So if you don't want to be in the exit lane, you best be moving. So this is something you should be paying attention to. But the way this task is presented is each of these pictures is shown for 280 milliseconds followed by a blank screen. And then it's shown twice, and then the new picture is shown. And so it's like, and what happens is the blank screen just swamps out any of the local orienting cues that would direct your attention to the change. So change has to proceed very slowly and serially around the picture. So these things take several seconds to solve, even though if we took out the blank screen, it would be instantaneous. So the speed with which someone can find these changes is thought to be indicative of someone's ability, and we can manipulate the changes in various ways to make this task more difficult. So the way that I had designed this task is I measured the amount of clutter in the screen. This was like a rating thing that I did with a bunch of pilot subjects, whether the change was relevant to driving or how relevant it was. So this is an example of a highly relevant change. If I had, taken out one of the trees in the background, right, you probably wouldn't be paying attention to that very much. That would be a less relevant change. How bright it was, so literally like the number of pixels that had changed, or the degree of change, you can measure that like in a, what's the word I want, almost in a mechanical way. And then another one that I ended up finding post hoc was whether or not the change was made to a sign. That turned out to be important. So in my dissertation, I had 155 older adults. I ended up keeping 36 items to show you as an example, and the outcome is accuracy. So here's the end of the story that your example is going to show you in greater detail. What happens if I treat the items as fixed and I don't have a random intercept left over, or I do have a random intercept left over in which items are treated as random, and I have allowed for the possibility that there are many other reasons why people would respond differently to these pictures than just the 4 things I have here. And I've highlighted the topic here. What do you see? What's the difference in the conclusions you would draw about the effectiveness of these item predictors? Everything's important, or just science. Which of these is right? Can I know that? Can I gain some evidence towards that at least? These are real data. Can you think of a way that you could decide empirically if you need a random effect?
Likelihood ratio test.
Boom. Yeah. Spoiler alert, I do. And so this column of results, it's not exactly the same results, but it's very close, are published in Educational and Psychological Measurement in 2005, I think. They're wrong. They're totally wrong. My notation in that article was god awful too. I looked back at it recently. I was like, oh, who published this? So yeah, that's why there's not a link to it like I would normally do for my sources. Don't read it. Don't read it. Just stop. I should like pull it from Google Scholar. Just stop citing it. like, I don't even want to do a retraction because, like, who gives a shit, right? This is, like, no one's ever used this task again except one person asked me if they could have it. I'm like, sure, go ahead. So, yeah, it's wrong. Because I didn't know, I did not have a linear models understanding of what I was doing back then. I had an IRT only understanding. And now this Lisa understands much better. So I can hopefully get you all to prevent making the same types of mistakes that I did. And I'll show you an example about all of that. So yeah, putting it all together. That's my summary. Go ahead.
Peeking on your dissertation is not probably the way to go, so, I mean, that's good, right? That you're learning.
I am learning. Yeah, we all do the best we can until we can do better, right? Like, and that's why I try not to throw shade at, like, articles from the 70s or 80s where they did things that nowadays would be like, like they did the best they could with the tools that they had. And yeah, it would be really sad if I didn't learn anything in the last 20 years. What I know now, I learned like 2% of it in graduate school in terms of my methods training. I barely knew enough to be dangerous. I picked up maybe another 10% over my postdoc, and the rest of it came from having to teach this stuff and feeling like I didn't want to be a fraud, so I had to learn it well enough to not be a fraud. And that has evolved over the years too. Question?
Yeah. So that's like something I kind of grapple with as I chug along in this master's program is like, there are tons of things I don't know and very little I can do without your help or asking questions, and like determining the degree of okayness versus like, you need to get it together, man. Like,
I think, yeah, if you don't know anything, then you learn something and you're like, I know a lot about this.
yeah,
And then the more you learn, you're like, oh, I did not know how much else there was
Right.
that I'm not privy to yet.
What is that, the Dunning-Kruger effect?
Maybe? Is that what it's called?
Yeah.
Dunning-Kruger effect? Any Zoomers, can you confirm?
It's like a curve that's like this in terms of like knowledge about a subject and like confidence about a subject.
I'm familiar with it in like a meme where like undergrads are like, I know everything about this. And then like you finish your dissertation, I know nothing. I know nothing. I spent the last 6 years on this topic and I know nothing. Could be Dunning-Kruger? Ask to Google?
that
Yeah.
is.
Yeah. I don't have an easy answer for that. I think that it's good to be appropriately skeptical about and hesitant to say that you know something. I think it's good to ask for help. I think that's a good thing. Because eventually you're going to be like, is this okay? And I'll be like, yeah. But until you get to that point, how else would you know that you're
Right.
not, it's not okay?
Right.
I don't think you should feel bad for not knowing things or needing help, because all of us, I mean, we're at different points on the journey. But you can't make progress unless you can find a way to do that, and help is one of the ways.
Right.
Yeah. So yeah, I did it wrong, but I'm going to show you all how to do it right. And I'll show you all how to do it right in 3 different programs, damn it, too. That's another thing that I've had to learn. This was back in the days, so. But that is going to happen next time, I think. Does that sound fair? Because it's 1:38. 20 slides in one class. That's pretty good. That's pretty good pace. Okay, so next time, then I want to show you all of the models that are presented in here. We'll talk about how to move between them, how to estimate them, how to interpret them. And then you have your very last lecture up. Do I have that up? Yes, I do. Lecture 8. I just threw everything that was left into one thing, and we're going to try and do it. The only thing I couldn't get in was power analysis, but I've got some resources for you that I have in articles here. So we'll start on example 7 next time, probably lecture 8 next week, and then I'll build an example to go with that. And I will let you know when your homework 4 is available with my feedback.
Great.
Okay? Okay, thanks for being here. Hang in there,
Hey,
folks.
Lisa,
Yeah,
Can I ask a question?
sure.
Other than